Humanity has always searched for new worlds. We crossed oceans, we crossed continents, and when we looked to the sky we found one, right next to us, a planet like Earth. Same size, same origins, same possibility. But when we finally reached it, we didn't find a second home. We found something else. This is Venus. Venus is often called Earth's twin. In size, mass, and composition, the two planets are remarkably similar. Venus is only slightly smaller than Earth. Its gravity at the surface is about 90% of Earth's. Both planets formed from the same region of the early solar system, composed of similar rocky materials. From a distance, Venus might be mistaken for a familiar world. But similarity in structure does not guarantee similarity in outcome. What makes Venus extraordinary is not how similar it is to Earth, but how drastically it diverged. Unlike Earth, Venus rotates extremely slowly. A single rotation takes 243 Earth days. Even more unusual, Venus rotates in the opposite direction of most planets. On Venus, the sun rises in the west and sets in the east. This slow rotation affects atmospheric circulation, heat distribution, and planetary dynamics. But the most defining feature of Venus is not its rotation. It is its atmosphere. Venus is covered by an atmosphere that is over 90 times denser than Earth's. This atmosphere is composed primarily of carbon dioxide. Cloud layers high above the surface are made of sulfuric acid. Sunlight penetrates these clouds only partially. The surface of Venus is never seen in visible light from space. The atmospheric pressure at the surface is equivalent to being nearly 1 kilometer underwater on Earth. Any spacecraft landing on Venus must withstand crushing pressure and extreme heat simultaneously. This dense atmosphere traps heat efficiently. Solar energy enters the atmosphere, but infrared radiation struggles to escape. The result is an intense greenhouse effect. This is not a mild warming. It is runaway. On Earth, greenhouse gases help maintain habitable temperatures. On Venus, the same mechanism spiraled out of control. At some point in its history, Venus likely experienced increasing solar heating. Water, if it existed, began to evaporate. Water vapor is a powerful greenhouse gas. As more water entered the atmosphere, temperatures increased further. This created a feedback loop. More heat led to more evaporation. More evaporation led to more heat. Eventually, oceans, if they existed, were lost entirely. Ultraviolet radiation from the sun broke apart water molecules. Hydrogen escaped into space. Oxygen reacted with surface materials. What remained was a dry, carbon dioxide-dominated atmosphere. The greenhouse effect became permanent. Today, surface temperatures on Venus reach approximately 465 degrees Celsius, hot enough to melt lead. And unlike Mercury, this temperature does not drop at night. The atmosphere distributes heat globally. Venus is uniformly hot. Understanding Venus required direct exploration. The Soviet Venera program achieved the first successful landings. These missions transmitted images from the surface before being destroyed by extreme conditions. They revealed a rocky, barren landscape under an orange sky. Later, NASA's Magellan mapped the surface using radar. Since visible light cannot penetrate Venus's clouds, radar became essential. Magellan revealed vast volcanic plains, massive shield volcanoes, and evidence of widespread resurfacing. Venus is geologically active, possibly even today. Despite its hostile environment, Venus remains dynamic. It is not a dead planet. It is a world still evolving. Venus today is defined by extremes. A dense carbon dioxide atmosphere. Surface temperatures near 465 degrees Celsius. Clouds of sulfuric acid. But these conditions did not necessarily exist at the beginning. Early in solar system history, both Earth and Venus received similar materials during formation: rock, metal, and volatile compounds, including water. The critical difference may have been distance from the Sun. Venus orbits closer, receiving more solar energy. In the early solar system, the Sun was slightly dimmer than it is today. Under those conditions, some models suggest that Venus may have been able to maintain liquid water on its surface. If so, it would have required a stable atmosphere and moderate temperatures. Climate simulations indicate that slow rotation, like Venus has today, could allow thick cloud formation on the day side. These clouds would reflect sunlight, reducing surface heating. This mechanism could have temporarily stabilized conditions. In this scenario, early Venus may not have been an inferno. It may have been a warm, possibly ocean-bearing world. But stability in planetary climates depends on feedback, and feedback can amplify change. Today, Venus has almost no water, but the atmosphere contains a clue. The ratio of deuterium to hydrogen, known as the D/H ratio, is significantly higher on Venus than on Earth. Deuterium is a heavier form of hydrogen. When water molecules are broken apart in the upper atmosphere, lighter hydrogen escapes more easily into space. Heavier deuterium escapes less efficiently. Over time, this process enriches the remaining atmosphere in deuterium. A high D/H ratio suggests that Venus once had much more water than it does now, possibly enough to form shallow oceans. Ultraviolet radiation from the sun would have played a key role. Water vapor rising into the upper atmosphere would be exposed to intense UV radiation. Molecules would split into hydrogen and oxygen. Hydrogen escapes. Oxygen reacts with surface rocks or is lost through other processes. This mechanism gradually removes water from the planet. The D/H ratio is not speculation. It is measurement. It provides evidence of a past that no longer exists on the surface. The loss of water is not the only change. It is part of a feedback system. As surface temperatures increase, more water evaporates. Water vapor enhances the greenhouse effect. More heat is trapped. More water evaporates. At a certain threshold, the process becomes self-sustaining. This is known as a runaway greenhouse effect. Once triggered, it cannot easily reverse. Even if the initial cause is removed, the system remains locked in a high-temperature state. On Venus, as oceans evaporated and water vapor increased, the atmosphere became more efficient at trapping heat. Eventually, the planet lost its ability to cool. Carbon dioxide, released from volcanic activity, accumulated in the atmosphere. On Earth, carbon dioxide is partially regulated through processes involving oceans and rock cycles. On Venus, without liquid water, this regulation failed. Carbon dioxide built up. Heat increased further. The atmosphere thickened. The surface temperature stabilized at an extreme equilibrium. Venus did not slowly warm. It crossed a threshold. And after that, the transformation accelerated. Today, Venus is in a stable but extreme state. The atmosphere is dominated by carbon dioxide. Cloud layers continuously circulate around the planet in a phenomenon known as superrotation. Upper atmospheric winds move faster than the planet itself rotates. This circulation redistributes heat efficiently. Unlike Mercury, where temperatures vary dramatically between day and night, Venus remains uniformly hot. The greenhouse effect operates continuously. There is no ocean to absorb heat. No vegetation to regulate carbon dioxide. No weather system capable of reversing the process. Future missions such as Veritas and Envision aim to study Venus's geological history in more detail. They will map surface deformation, volcanic activity, and internal structure. The goal is to reconstruct the timeline of Venus's transformation, not to imagine what Venus was, but to measure how it changed. Because Venus is not just a planet. It is a case study in planetary climate evolution. Reaching Venus is only part of the challenge. Surviving its surface is something else entirely. The Soviet Venera program achieved the first successful landings. These spacecraft were engineered to endure conditions unlike any other planetary surface in the solar system. When Venera landers descended through the atmosphere, they passed through thick layers of cloud composed of sulfuric acid. As they approached the surface, pressure increased rapidly. By the time they landed, the pressure reached approximately 92 times that of Earth's surface, equivalent to being nearly 1 kilometer underwater. Temperatures exceeded 460 degrees Celsius. Electronics failed quickly under such conditions. The longest-lasting Venera landers transmitted data for just over 2 hours. But in that time, they sent back the first images ever captured from the surface of another planet. Those images showed a landscape unlike anything on Earth. Flat, rocky terrain. Scattered stones. A dim orange sky. Visibility was limited. Light was heavily diffused through the dense atmosphere. The surface of Venus is not bright. It is muted, heavy, silent. Radar mapping by Magellan revealed the true nature of Venus's surface. It is dominated by volcanic features. Vast lava plains cover much of the planet. Shield volcanoes rise above the surface, some hundreds of kilometers across. One of the largest, Mont Mons, stands several kilometers high. Unlike Earth, Venus does not show clear evidence of plate tectonics. There are no moving continental plates. Instead, the surface appears to have undergone global resurfacing events. Large portions of the planet may have been covered by lava flows in relatively short geological periods. This suggests a different internal dynamic. Heat builds beneath the surface. Without plate movement to release it gradually, pressure accumulates. Eventually, it may be released in large-scale volcanic episodes. Recent observations suggest that Venus may still be volcanically active. Changes in atmospheric composition and surface features hint at ongoing eruptions. If confirmed, Venus would be one of the few planets in the solar system with active volcanism today. Conditions on Venus's surface remain constant. There is no day-night temperature variation. The thick atmosphere distributes heat evenly. Unlike Mercury, where temperature swings are extreme, Venus is uniformly hot. The atmosphere acts as a thermal blanket. Pressure compresses gases near the surface. This compression contributes to heat retention. The result is a stable but extreme environment. Any material exposed to the surface must withstand high pressure, high temperature, corrosive atmospheric chemistry. Future missions must overcome these challenges. Traditional electronics fail quickly under such conditions. New materials and cooling systems are being developed. Long-duration surface missions on Venus require entirely new engineering approaches. Exploring Venus is not just about reaching it. It is about surviving it. Venus is not static. Despite its harsh conditions, it remains geologically active. Evidence suggests recent lava flows. Possible atmospheric variations hint at ongoing volcanic activity. Future missions, including Veritas and Envision, aim to investigate these changes. They will map the surface at higher resolution. They will study tectonic deformation. They will search for signs of current activity. Understanding Venus is critical, not just as a planet, but as a warning. It demonstrates how planetary climates can evolve into irreversible states. It shows what happens when greenhouse effects become uncontrolled. Venus is not just a neighbor. It is a lesson. A planet that may once have been similar to Earth, now locked in a state of extreme heat and pressure.